Welcome to the Clojask presentation. My name is Matt Buehlmaier, and together with Yuchen, we are going to present Clojask, a data processing framework with parallel computing on larger than memory datasets. I would like to begin by giving you a brief introduction about the motivation why we built Clojask. So most of you are familiar with data.table or dplyr in R, pandas or Dask in Python, and Hadoop MapReduce in Spark. Broadly speaking, those libraries or frameworks can be categorized into two different groups. The first one is in-memory data processing, where you hold the whole dataset in computer memory. The advantage is that it's fast, but the disadvantage is that your dataset cannot be too large because it has to fit into computer memory. The second group is for larger than memory datasets, where you can process the dataset maybe on a computer cluster or on your own computer in parallel. But the drawback is that it's often difficult to set up, and there are many optimizations, so there are lots of parameters you can choose from to make it even run better, so it takes some time to set it up. For us, for Clojask, we wanted to find a middle ground, where on the one hand we can process datasets that are larger than memory, but on the other hand, it should be easy to use and easy to set up, and it should be work straight out of the box. So to this end, we chose to use Clojure as a programming language because it runs on the JVM, and moreover it has a very, very long and distinguished history, having influenced many other programming languages. So in a way, we're standing on the shoulders of giants, building on all the other work that previous people have done. So, and on top of that, we can also leverage the Onyx platform, which makes it easy to parallelize the computations and distribute them. So the design goals were threefold. Number one, as we mentioned, it should be easy to use and easy to set up, and basically just work out of the box. This is especially important for data scientists like us, who basically just want to analyze their data, but do not want to deal with a lot of installation or setup or optimization issues. The second design goal was that it should work on datasets that are larger than memory. So of course it can also work on datasets that are smaller than memory, but specifically it should also include datasets that are larger than memory. And so to this end, we chose a very specific design approach where we are basically streaming through the whole dataset once, if possible, and we hold the minimum possible amount of data in memory at any given point in time. The third design approach was that we wanted it to be fast. So we wanted to make sure that it works in parallel, so some computations could easily be conducted in parallel, and we wanted it to be transparent in the sense that the user does not really have to worry about that, and it works basically automatically almost. So it works very well on a single machine already, and we have also a proof of concept to run it in a distributed mode on a computer cluster with a distributed file system. Having said that, this is still work in process, so the computer cluster distributed version will be released in the future. And so if you would like to learn more about Clojask, please feel free to take a look at our website. There's a lot of documentation out there, and you can also find us on the Clojask channel on Clojurians on Slack. And last but not least, if you would like to give us a star or file an issue, feel free to check out our GitHub page. So thank you very much, and without further ado, I'm going to pass the time to Leo. Thank you.
Thank you, Dr. Buehlmaier, and I'm Yuchen Liu. I helped develop Clojask under the supervision of Dr. Buehlmaier at HKU. When designing the APIs of Clojask, the top consideration is to make it as intuitive and straightforward as possible, so that data scientists having prior experience with SQL and R before can adapt to Clojask really fast. The learning curve of Clojask should also be flat. And here is a syntax comparison between SQL, R, and Clojask. In SQL, you can have this simple query statement. You can select 2 columns from this data table, and there's this corresponding R data table implementation of the same logic using the square bracket syntax format. Also, here's a group by and aggregate query for both the SQL and R data table. Users find both SQL and R easy to write and easy to debug. That's what we want to replicate in Clojask as well. So to do the same thing in Clojask, here's the code. You can see there's much similarity between SQL procedure and Clojask. You can see a clear correspondence between the filter function in Clojask and the where statement in SQL, as well as the select in SQL and the select option in the compute function in Clojask. Also, for the group by and aggregate, the group by statement corresponds to the group by function in Clojask, and in Clojask you can aggregate aggregation functions on different columns as if in SQL. I'd say programming Clojask is interesting. Considering Clojask is a distributed data frame, it is not easy. Previously, there is this stereotype about distributed computing. On one hand, distributed computing is considered to be scalable, resilient, and have high throughput, which backend developers love about. Data scientists may find them cool and exciting, however, many of them cannot take the full advantage of these properties. On the other hand, anyone inexperienced with distributed computing before will be faced with complex installation issues. It is even hard to write a hello world program at first, and the overhead to create new jobs is relatively high. That's why many data scientists prefer to use R. Data table library should take most of the credits here. In R, data scientists typically set type on data table columns. They can map functions on columns and even filter on rows, group by on columns, and reduce on them. Basically, they can code freely as they wish. In summary, I think there are 4 important features about R data table. First, the computation is run in memory for the input as well as the computation process and the output. And each operation has an immediate return, leading to this sequential programming mode that if you call different operations in different order, then of course the result will be different in consequence. And at most of the time, R will run in a single thread. Although there are some advancements in R recently that may change this situation. However, for a distributed data frame, things are totally different. Instead of running in memory, different distributed platforms have different memory allocation strategy, and users typically do not have control on them, and the strategy is not well documented on some websites. And instead of an immediate return, functions will return lazily, only if the user calls certain final compute or execution function, similar to lazy sequence concept in Clojure, I'd say. And third, users normally have constraints on their programming. For example, they may be asked to implement certain interface or make their customized class serializable or something like that. This is because their program is meant to be compiled to a executable file and distributed to different machines, because a distributed data frame can be ran in multiple threads or a cluster of computers. In terms of the real execution process, different rules are first translated and construct a directed acyclic graph of rules that can be applied to each and every columns. And there will also be an environment with idle workers. The rules as well as each part of the data frame will be allocated to the idle workers. Here I just demonstrate a ideal and simplest case of distributed computing. After computation, the worker nodes will pass the results to the output data frame, which will be either in memory or in a distributed file system or even in the local file system, depending on different platforms. Clojask, as I said, is also a distributed data frame. So in terms of the data flow, it has no difference as a normal distributed data frame. However, when we design Clojask, we focus on three things additionally: usability, large datasets, and performance. You may associate the last two together, so we really focus on performance on large datasets. Clojask is not perfect. What I mean is, for a small dataset, which roughly speaking is hundreds of megabytes, Clojask may not have advantages over other excellent libraries in Clojure out there. Clojask is really designed and optimized for datasets larger than memory. So instead of a uncontrolled memory strategy in a distributed data frame, Clojask will use the minimum memory in all of the computation steps. For example, if you are just running a row-wise operation, then Clojask will only load a few rows needed at a time in memory. So it will traverse the dataset as a stream to support a really large dataset. And instead of this lazy return, we can have a partial preview for many lazy operations. This result is generated by sampling the first few rows of a data frame. We cannot 100% guarantee the accuracy of the preview and the actual output, but at least it can give you a sense of what you are dealing with. And then we believe the biggest advantage of Clojask is that you can basically program as you wish with minimum constraint. And we will talk about it in detail later. Lastly, Clojask right now only supports running on multiple threads. It does not support deployment to cluster right now. However, we did try to incorporate Clojask with distributed file system, and we are making some progress. However, we are still some way before enabling Clojask on a cluster. We have made considerable technical decisions to make Clojask different. First, one of the constraints we want the user to know is operations are evaluated in a preset order. So that is to say, although you call, for example, set type first, map function second, then filter, in the real execution, filter will still go before map functions. Actually, the real order is first set type, then filter, next map functions, next group by, and finally reduce. This order is inspired by the optimization theorem in databases. So this is to guarantee that user can still do most of the things they want, but maintain a high efficiency. I would like to elaborate on the concept of execution rules by a brief API walkthrough. But I won't demonstrate the APIs at this presentation. If you are interested in a API demonstration, you can visit this link on our official website. I would like to further elaborate on this concept of execution rules. Although users are allowed to call functions at any time, we do suggest you to call functions in the same order as its execution order in order to reduce confusion in the future. That is to say, the first stage in the execution is the initialization. So you are suggested to call dataframe to define a Clojask dataframe first. And then it's time to set type on different columns using function setType or setParser. And then you can filter on rows using the filter function. You may even call multiple filter functions in order to get an intersection of results. Next, you may operate or map certain functions on a column or multiple columns as a whole. After doing all this, you have three options now. One is to group by, another one is to aggregate, the other one is joining. Actually here, grouping by and joining are mutually exclusive. But if you want to join on the result of group by and aggregation, we suggest you to first get the result of group by and aggregation, then join on the results. Of course, you can call aggregation after group by, which forms this group by aggregation classic combination. Finally, do not forget to compute, which is to get the actual result of all the previous lazy operations. Let's go back to the technical decisions. In order for Clojask to support really large datasets, we will only load the top few rows of a dataset in memory for previous purposes. And also, instead of a rules DAG, we will construct a rules hash map, which will do less than a rules DAG. However, for a normal use case of a data scientist, it will not make a big difference. This consideration is made by a compromise to traverse dataset as little time as possible, because we are expecting a large dataset, so the overhead of traversing it once is high enough. One of the biggest advantage of Clojask is the autonomy in programming, and this is enabled by the inter-thread communication between worker nodes. Function definitions are passed to worker nodes at runtime, so no more compilation, no more programming constraint on function definitions. Hurry! Finally, the output data frame will be directly written to the destination file for a large dataset to reduce memory consumption. Here is a benchmark comparison between Clojask and Dask. Dask is on the left and Clojask on the right. You can see in this table, in terms of element-wise operation and row-wise operation, Clojask outperforms Dask in all of the test cases. However, in others, for example, group by aggregate and join, Dask performs better in smaller test files, for example, the 1.8 million and 3.6 million case. This is because when the file is small, Dask will load the dataset in memory, and so in group by aggregate and join, it will not frequently input and output from file. However, in Clojask, we will by default read and write intermediate results to external disk storage. That's why we perform slower in these cases. And this is the reason why I do not recommend using Clojask for smaller datasets that can reside in memory. And here's the function comparison between Hadoop MapReduce and Clojask. Basically, Clojask can do most of the things Hadoop MapReduce can do, except for deploying to a cluster. For Spark, Clojask and Spark have a lot in common. First, they both have this concept of smallest computation unit. In Spark, it is called RDD or data frame or dataset. In Clojask, we call it data frame. And both of these units are immutable. In Spark, it can construct operations DAG, which we do not. Also, there is a trade-off between caching intermediate results in memory in Spark and our minimum memory usage strategy. This is a technical trade-off, and you cannot say which one is better. Finally, I would like to discuss a few outlooks for our project. We would like to mainly work on 4 things. First, we will try to incorporate distributed file system to Clojask in order to deploy Clojask onto a cluster. Next, we want to add more data analytics functions to make Clojask more comprehensive in terms of data analysis. Then we want to support more file types, probably Parquet and Afro in HDFS, and even support database in the future. Finally, we would like to appreciate Onyx, which is a popular distributed platform written in Clojure, and we use it as our default distributed platform. Although it has not been actively maintained anymore, we would like to improve on that for our purposes to mainly increase the throughput of it. That's basically all for my presentation today. Hopefully you can find it interesting and helpful. And we will also be here in the later Q&A panel, and see you there.